Right, I think it's live now. Let me know if it's coming through. Okay, good. I just want to make sure because sometimes it doesn't show up. Oh, it's working here anyway. I can just check. Getting lag. What's wrong with this thing? Look at that. Right. Anyway, just mute this a minute. Right. Okay, there's the frequency on the scope. Oh, sorry, it's kind of, yeah, hard to see. I seem to have got my things look a bit cockeyed underneath here. Try to lift it up a bit. That should be a bit better. Right, yeah, you can sort of see it. Right. Oh, current consumption on the secondary coilers on this meter. Oh, this is in the way as well. Can't really move that all the way. I'll just try to elevate my meter a bit or something. I don't know. What can I put underneath? Ah, this should work. Need that wedged a bit more. That should be. Oh, I'm getting too high now. I'm getting near the edge of the blooming video. Oh, I'll find something that's not too. Anyway, as long as you can see it, it's just a bit obscured. What else can I put underneath there? I'll just stick this pad underneath. That should just give it a little lift. Right, that should be a bit better. Right, 8.8 milliamps on the secondary coil right now. I can show you the waveform on the output coil as well. I'll push this down to, that's the output on the secondary coil, but it's on a low out. It's loaded down right now by the meter. When I unplug this current meter, you'll see what I mean. The waveform jumps right up now. That's the output waveform without a load, and that's with the load. Right. So now that's the power in. 43.5 milliamps. Sorry about that smudge on my meter. I went and spilt some bloody acetone on my bloody meter. That's why it's gone like that. I need to maybe sort of get a new glass for it or something. But anyway, the current input is 43.5 milliamps. Right, that's any better. Oh, that's dark now. Anyway, it's 43.5 milliamps in. Now, okay, that's good, as long as you can see fine. Right, right, so at the moment it's 8.7 milliamps, but I had it earlier at 9 milliamps, so I'm just going to tune it a little bit, because I might put that back onto the input waveform, to get that locked on again. What's got wrong? That's both. Need to tune that, get that locked. I'm using the internal trigger right now. I'm not using an external trigger. Anyway, let me just tune that back so it's about 9 milliamps. Tune this other one a bit. Around about here though, it just seems to be fraction out. Just getting it finely tuned is fiddly. I've ordered some more trimmers as well. Oh, that's near enough. Well, it was 8.9 just then. I've ordered some more trimmers that are plastic caps, so that when I put my screwdriver in it won't affect the setting, because these metal trimmers are a pain. So I've ordered some more trimmers as well, 100k, and the plastic tops, so I can use my metal screwdriver without affecting the tuning. Anyway, 8.9, that's near enough. Now, watch the current input to the circuit. Now, it's going through my meter, so when I put the meter on hertz, it will stop the output, the power will go off. Right, there you go, power went off because it's going through the current on the meter, right? So, okay, right, that's reading 43.8 milliamps right now. Okay, now if I take the load off the output coil, which I've done now, you can now see it's reading 43.7 milliamps. So it's literally only using 0.1 of a milliamp when I'm shorting the output out. So the output is pulling it down by about 9 milliamps at half a volt. So I'll go to volts. The volts output is 0.508. That's half a volt, just over half a volt. It's actually about half a volt, that. So no, this is locked again. There we go. I like to tune it so I'll get it locked on both of these, really. That's better. Locked on there. Oh, I'm not locked on there now. Fiddly tuning this when I'm not using an external trigger. anyway, you can see what I mean about the instead to explain this waveform a bit better, let me just get this bloody locked because it's not locking yet. I have to change this setting on here. Want to be on, let's try that one. It's the coupling that affects it. Some coupling's better than others. Try the TV setting again. Depends on the waveform output, what kind of lock you can get on it really. It's sort of shifting slightly. That's not bad. But anyway, we're at we're 0.509, which is about half a volt AC coming out the secondary coil. I'll lift it up just a bit so you can see better. But it's yeah, that's the output of the voltage, and that's the current input, 43.7. And I'm going to put this back on current. Milliamps. Now it's drawing 9.1 milliamps out, and watch the input to see what that's changed to, which is 43.8. So that's literally 100 microamps of input variation. And not forgetting the fact that I'm actually driving this circuit now at 43 milliamps. That's including the voltage regulator, the NE556 timer, all the biasing resistors. The actual coil itself is actually drawing a fraction of that. It's actually something like I think it's 15 milliamps or something, or 20 milliamps. So I can't measure it easily now because it's on this board. But yeah, the actual coil is, oh actually I could put an AC thing in series, but that means I'm measuring both the ground wires, as you know. But it's actually drawing a lot less current. I mean, remember if you found the AC transformer, I mean 350 milliamps on AC what this thing was soaking up, and this was getting really hot. Well, not hot, but it was getting warm. Do you remember the coils were actually getting warm before when I did it on that transformer? Well, they're stone cold now, actually, absolutely stone cold. So there's no heat waste, there's no heat loss in the circuit anymore, in the coils and actuation coils. They're not wasting heat now, wasting energy than that. And so I got back to 9.1 milliamps output on the AC, and it's 43.8. As I say, I put dual, that's the output from the coil when it's loaded down. The output of the coil when it's not loaded down, when I take the short out, is that. So that's the output from the secondary coil. I'll put it in the middle a bit. So that is the output on the secondary coil. That is the input on the two actuation coils. Output, input, output. Now if I load it down, it collapses obviously because it's under a short circuit load now. It's back at 9 milliamps. I can increase the gain on here so we can see it still. So that's the output coil. I'll leave it about there, otherwise it gets, if I take the load off, it just gets a little bit overwhelming. Actually, if I take the load off, it gets really overwhelming. But that is basically what's coming out anyway. So I've got back on input. I've got them both all wired up the way you wanted me to before, when you asked me to hook up the second channel to the output coils. Well, that's all wired up now. So anyway, it's very encouraging, and obviously my magnetic switches are giving me a huge amount of separation. So the load that we put in, the actual input power that we're putting in, we're actually getting a good separation now between the input and the output section, because we're not seeing much of a difference on the loading. So that's the reason why we're only seeing 100 microamps instead of a much larger difference on the input. So it's definitely working. It's just I need to get the secondary coil and the laminations. I need more laminations, and I also need more turns on the secondary coil to get more voltage out. So that's the obstacle right now. That's why I want to build the square one. I've updated my schematic a little bit, but that's the reason, as explained, why I want to build this square one. Because there's a lot more laminations though side by side, and we'll get much stronger magnetic flux switching through to the secondary bobbins. And anyway, that's the reason why I need to build this one, because this one, the laminations are like 10mm apart. Each pair of laminations, that's 2mm laminations going through here. Then there's 10mm gap. There's a 10mm gap. Then we've got another 2mm laminations there. Then there's another 10mm gap. So the amount of waste, the amount of decoupling that's happening there is huge, really. That's why if we have them all stacked side by side, we'll have much less loss and we'll have much more gain. I'd tilt this all up, but I'm just worried about pulling wires out at the moment. Actually, got half a volt. 1K is a bit too high. I think we really need something like a 10 ohm resistor. I've got a 10 ohm, there's a 100 ohm resistor there. I've got a 10 ohm resistor, let me just find one, just a minute. A 10 ohm would be much better for the, it's divided by 100, so because we're on a low voltage, we need a low resistance. I'm pretty sure I've got some low value resistors in here. I'm just finding my meter's hooked up to the current right now, so it's a bit fiddly. Let's see. Oh, here we go. 10 ohm resistor, I think. It's brown. No, hang on. That's brown, black, blue. Oh, that's not 10 ohm. That's like 10 mega ohms. Brown, black, black. There we go. Brown, black, black. That's what, 10 ohms, yeah? Right, let's just measure. I'll measure this on my meter quickly because I have to. I'll have to disconnect the series thing. Just a minute. Well, I'll just connect these two together a minute. Right, I've bypassed the meter for a moment, and I've knocked the power lead thing. Right, I want to just check this is a 10 ohm resistor. Verify it. This is the resistor. Right, it's 11.7 ohms. Right, I've knocked the power off on that thing. I've got one of the jack sockets I'm connected to these. Right, that's 11.1 ohms, so I'll put this back on current. I'll put this back on the power. Right, that's positive in. Back on it, that's it. I've not got flipping wire. Right, okay. Now we're 9 milliamps on the output. Now what I'll do is I'll stick the 10 ohm resistor onto these leads. Right, I've got these leads. Watch the current, 43.9 milliamps. Right, I'm just bending the resistor around. 43.9. Right, it's gone up to 44 now. So that's exactly 100 microamps. 44 milliamps right now. Take it out. So that is 43.9. That's with a 10 ohm real power resistor, as that's what C, so that's real, measuring real power. So it's 10 ohms, 44 milliamps. I'll check it out. 43.9. It's actually hovering a bit between 43.9 and 43.8, which is that's a little bit, yeah, that's negligible amount. Yeah, well, either 100 or just a fraction over 100 microamps, or even 200 microamps, it's still very good. Right, we're back on 10 ohm resistor. 43.9, check it out, 43.8. It's actually drifted slightly, that's why. It's drifted down a little bit on output, so it's actually still 100 microamps. Resistor into these two sockets here. 43.9. Check it out, 43.8. Now I'll stick this straight back in the meter. There we go, it's reading 9 milliamps. Got loads of resistors all in this phone. It helps you to find resistors quickly. Instead of them being lying around in the bottom of a tray, I can go around, measure each one individually with my probe if I can't read the value, and it's quick and easy way of finding a resistor. That's why I keep all my loose resistors, the small ones anyway, not really the big ones because they take up too much room. Yeah, it's 100 microamps, yeah. And I think that's really, really good. So we've done the test. We've done the test now with a 10 ohm load, and I'm sure Z can work out power factors and all that, but it's the coupling that obviously is the problem right now, because I need more coupling really. And my board is, look, I've got the heat sink on it, look. I don't know if you can see it. I'll try and get a bit of light on it. There's my heats. These clips are clipped onto the test point. That's the oscilloscope. The red lead is clipped onto a test point which I put in the board for testing the. That's what's going to the oscilloscope right now. So, and I've got a big power transistor which is on the edge of the board there. So anyway, it's working, and all mounted on the heatsink. The power output stages are mounted on the heatsink. I actually put some epoxy glue between the heatsink and the circuit board to hold this end of the heatsink on here, so it doesn't slide around, because it was just resting on the board. So now it's anchored to the board at this end. And the heatsink is stone cold, by the way. I mean, well, it will be at 43.9 milliamps. It's hardly drawing any power, which is what I want. It's very efficient. We're not wasting power. That's the thing. So I mean, it's actually cold as an Eskimo's ass, as they say. So yeah, it's going to be fun when I get my new device built and start driving it from this circuit board. Yeah, we're going to have fun. And also when I get these new pots, I'll change these pots, because the 47K's in there right now. 100K pots will be a damn sight better than 47, because I'll be able to have a much wider frequency tuning. I'll have much more frequency drift for tuning than I've got with the 47s, because the 47s only gives you a 47K differential tuning, but 100K I'll be able to go a lot further, sweeps. I'll be able to get much better frequency change adjustment. Obviously, the problem with the 47K pot is it tempts you to want to change one of the capacitors for a lower value, or a capacitor for a higher value or something. And having 100K pots, it eliminates that need to keep changing your capacitors. You know, I certainly don't want to be doing that if I can help it. Yeah, oh, you mean put a different meter on the output? Well, yeah, I could stick this meter on the output. I've only got 2 digital meters really, but we've already put it through a 10 ohm resistor, haven't we? I didn't actually look at the scope though. Let's have a look at the actual scope output when I'm loading the secondary output down. So let's switch this back to the output. Now I'll switch this to a reasonable setting. Let's put a 10 ohm resistor across this waveform while we're looking at the oscilloscope and see what that does. Right, 10 ohms. There we go. Now that's the actual output on the scope with a 10 ohm resistor across that coil. I'm taking it out. Well, but we're looking at higher range though. Let's go down a bit so we can see more of the waveform when it's not loaded. Now I'm going to put the 10 ohm resistor on it. Right, there we go. That's what it drops it down to. And all this time you'll be able to see what's going on with the input. Oh, hang on. I'm connected now. So 43.9 with this resistor, take it out. 43.8 without it. Anyway, a 10 ohm is certainly better than 100 ohm, because you wouldn't see much of a change at all with 100 ohm because of it being at half a volt. Right. Well, to be honest though, the resistor test is. Oh, you want me to swap the meters around? Well, yeah, I could do that. Yeah, I could certainly do that. I'll put this meter on the input. It's going to be harder to read, it's smaller. Oh, you don't want me to put this meter on the input? Oh, I'm not sure what you're on about then. All I have to do is swap these leads around. So if I take this meter off here, right, and then unplug this meter, right, and then stick this in the milliamp, right, that's showing, oh, on AC right now, that's DC. Right, DC, hang on, it's not, it's just calibrating itself. DC, we're at 43.5 milliamps, that's what's reading going in. This wants to be on AC. And this one is reading 9 milliamps, it's the same as the other one. So they're both the same. So this one is reading 9.1 milliamps being loaded down. So let's see it. Oh, hang on. 9.1 milliamps on the secondary on this meter now. It's a bit small. It's hard to. Well, I'll let it pass down. Now we got 9.1 milliamps is on the coil, so it's really the same. Both meters are exactly matched. You know, they're both accurate. That's the output. Output is no longer shorted. Input now. This is input now. 43.2 milliamps going in. It hasn't even changed on this one. Oh, I am on DC. Yeah, this one's not even showing the change. Actually, that's weird. Oh yes, it is. 43.3. It's actually gone up, actually, without a load on. No, it hasn't. 43.4. Now it's gone up to 43.4. Right, with the load on. Load off. Oh, it's settling down. It's not stable yet. Load off. It's gone down to 43.4. Load on. It seems to be hovering between 43.4, 43.5. No matter what I do, it hasn't settled down for some reason. Load on. 43.5. Load off. This meter's a bit slow responding for some reason. I think it self-calibrates or something, I don't know. Oh, it's gone down, yeah, 43.4. It's just sort of hovering on that edge. 43.4. Put the load back on. And it's gone up to 43.6. There must be some frequency drift on the circuit maybe because I've had it off and on. Yeah, it's really 43.6. Load off, 43.5. It's definitely 100 microamps. Definitely 100 microamps difference anyway. So, I don't know what else. I wasn't quite on the light, was I? 100 microamps anyway, difference. Anyway, I'll swap these around again. I must have been back on AC. I've got a bad connection down there. I'll pull the wire off somewhere. There we go. Right, input. Can't get a lock again. There we go. So, you said no, what exactly is it you want? Hang on, let me just read back. You still want me to put a 1k resistor across it? It's not going to make much difference. I mean, at half a volt, a 1k is 1000 ohms. It won't make no difference, I can tell you. I'll get you a 1k resistor. Let me find one. I'll find you a 1k resistor. But it won't make no difference. You won't even see a change. I need my meter back. Hang on a minute. I keep knocking this bloody wire. I hate these. I've got these wires clipped onto this stupid phono plug. This phono plug is made in China or something, and it's just very bad. Right, let me find a 1k. I'll leave it there so you can read it. Right. I want this on the 2k range. We're on the 2k range, so it will only read stuff when I'm on a 1k resistor or below. Let's find a 1k. Let's just check it's working. Yeah. Right, I need a 1k resistor. That one. There you go. Oh, what is it? 1k. Found your 1k resistor. Right, hide. 1k resistor. Oh, hang on. No, it's not a 1k. That's weird. It was reading 1K, no it's not. So, hang on. No, it's not a 1K that. It must have been connected to a resistor underneath. There, that's a 1K. Right, okay, we found a 1K resistor. .002 or 1.001 actually, because I'm touching my fingers so it's affecting it. 1.002, that's 1K. Right, I'll put those over there. I need to put this back on the current. Put this back on in the circuit. Wrong wire. Where's the other one? I'm not the bloody power again. Positive in. Come here, bugger. Positive in. And a positive to the meter. Right. Bad connection there. Right, okay. We're running again. 1K resistor. We're going to stick this on this meter now. Right, I'll go on the secondary output coil. That's the output coil. Right, what's the reading on this meter? I'm not in the hole. I am now. It's not making any difference, it's too high a value. 43.9, I've got this resistor in here. Check it out. Well, it's 43.8. Put it back in. Oh, it's got those little the plugs in there. They've got them little cross slots, and you can stick them inside the slots. Actually, you know those little split pins. I can stick the resistors right in the middle of those split pins. Right. Right, the 1K resistor is connected to those terminals right now. Okay, well I've got a 1K resistor now. It's not going to make no difference, and it's not because it's too high a value. The 1K is in, that's the output coil waveform. I'll take it out. You can see a slight change, but not much. But there's no change on the actual input current at all. 1K is just too high value. Let me just alternate it a bit. On and off. Can't see any change on the scope at all. We're measuring output coil right now. Let me stop it scrolling a bit. Right. These legs are a bit thin, they keep bending. Right. You can see it moving a little bit, look. and I put a load on this 1k resistor on it, you can see it gets a little bit smaller, not much. I'll hold it on. The input is 43.8, took it off, 43.8, it's not moving at all. That's with the 1k resistor. Right, I'll stick this back in here. And now we're seeing a big difference actually. I've got both beams on right now. I thought I was only on one. No, that's the other one. Yeah, well, yeah, I didn't see much of a change. That's input waveform. Can't seem to get a lock. You know what I need to do when I make another board? I need to build a capacitor into the board for an external for the external trigger circuit for the scope. That's probably another option to do. I have a little capacitor on the board so I can just clip the external trigger directly to it, and because it saves, otherwise you have to try and find a point to solder something onto, and it's just a lot of messing about. That's probably an idea. So I've been looking at my circuit. Oh, Alan's here. Alan posted some messages on my live stream. Yeah, I'm going to build another capacitor in for the for an external trigger. Actually, I need to go and get some food. I'm planning on going to get fish and chips tonight. Actually, don't tell Shubas. He always criticises me for eating fatty foods. But it's over a week since I last had some, so I didn't get that very angled very well, did I? I think I'll save this as a test video. I'll save this as a test video, I think. Well, I've already done a 100 ohm test at Hyde. I did that before, and 100 ohms too high as well. 10 ohms is about right for this voltage. A 10 ohm load is pretty good for half a volt. AC and I've already done the 10 ohm test, you know. I did that earlier. That's what I started off with. 100 ohms is also too high, really. You don't see any change. The 100 ohm doesn't display any changes on the input at all. That's why I had to go down to 10 ohm. Even 1K doesn't show anything. I mean, the higher the resistance, obviously, on the load, the less of an impact it's going to have on the circuit. So, ideally, a 1 ohm resistor, but even so, even shorting it out completely, it doesn't show anything more than 100 microamps difference. Anyway, I'll stop the video, I'll save it because then I can refer Alan to it later.